The goal of this week is to teach you about a very important function, which is really more like a design pattern called reduce. But in order to do that, first we need to talk about a tiny bit of abstract algebra. That sounds very scary, but it's not nearly as difficult as it sounds, and I'll take it slowly. So what we need to talk about is something that I've been repeatedly hinting at for weeks and secretly showing you a lot of different examples. So it's finally time to identify this pattern and give a name to it. The thing in question is operators for which bracketing doesn't matter and which have a neutral element or a do-nothing element. So here are some examples that you've seen. Addition of natural numbers with 0, multiplication of natural numbers with 1, the AND operator on Booleans with true, the OR operator on Booleans with false, the AND operator on propositions with true, the OR operator on propositions with false, concatenation of lists with the empty list, times of regular expressions with the regex I, and plus of regular expressions with the regex Z. So there's lots of examples. These are all examples of a common pattern. The name that we give to the general concept is monoid. So for example, there is a monoid of natural numbers with addition and 0. And there is a different monoid of natural numbers with multiplication and 1. There is a monoid of Booleans with and true. And there is a different monoid of Booleans with or and false, and so on and so on. So in ask, I can package the data of a monoid into a data type. I can write data monoid A, and then I have to say, and I can say make monoid, and then I have to give two pieces of data, an element of A, which is the neutral element, and then a function that takes two inputs from A and gives an output in A. So for example, now I could say, I could define plus for natural numbers. So let me define the natural numbers. And then here's the plus function, which you've now seen lots of times. N inductively M. 0 plus n is n. And successor of m prime plus n is the successor of m prime plus n. So now I can say addition is a monoid on the natural numbers, and I can say define addition is make monoid, and then I have to say what is the neutral element, which is 0, and then I have to say what is the operator, which is plus. Now, every time that I say that something is a monoid, there are three proofs that I should write. This is part of what it means to be a monoid. So, namely, that if I apply the operator with the neutral element in either of the two inputs, then the other input stays unchanged. And then a third proof that says that the two possible ways of bracketing three things are equal. So that means that for the addition monoid, I need to say prove that 0 plus anything is itself, prove anything plus 0 is itself, and then prove that the two ways of bracketing addition of three things, so L plus M plus N equals L plus M plus N. So if I can complete all three of these proofs, then I know that this is actually a true monoid. And I'm not going to write these proofs in this video, but these should be completed. So these are all true facts about addition of natural numbers. Okay, so let's do another example. I can define the Booleans as true and false, and then I can define the AND operator on Booleans. Say from A, and then I can say that false, and so here's the fast way of defining AND. I can say false and anything is false, and true and B is B. And now I can say and is a monoid on the Booleans and define it to be make monoid of the neutral element for and is true, and then the operator is and. And then in order to know that this is really a monoid, I need to say prove true and anything is itself, prove anything and true is itself, and prove the two ways of bracketing are equal. Okay, let's do one more example. Here is the data type for lists. Data list A is empty or a cons list A. And then here is list concatenation. Say you've seen this a few times as well. Define x's plus y's, inductively x's. From x's. Then empty concatenate y's is y's, and tail concatenate y's is head concatenate y's. Now I can say that concatenation is a monoid on lists, and I can say define concatenation equals make monoid, the neutral element is the empty list, and the monoid operation is concatenation. I made a mistake. So, yes. There we go. And in order to know that this is really a monoid, then I have to write my three proofs. I have to say prove empty concatenate anything is itself, prove anything concatenate empty is itself, and I have to prove that the rebracketing equation is true, which is this. So in each of these cases, you will be, you need to write these proofs. Now, they need to actually be proven in order to know for sure that this monoid is really a monoid and it's not just faking it. So you'll be doing a bunch of this in exercises. So hopefully that's enough different examples that you can start to see the general pattern. It's also worth mentioning some non-examples, some things which are not monoids. So obviously anything that doesn't fit the pattern of a function with two inputs and a neutral element obviously isn't an example. So something like snuck, which takes a list and an element and joins the element onto a list. This is not an example because this function doesn't have the right shape. Its two inputs are not the same sort of thing. So this, you can't make a monoid out of this. A more interesting non-example is something like subtraction, because for subtraction, the rebracketing equation isn't true. It's not true that if you define subtraction correctly, it's not true that a minus b minus c is a minus b minus c. You can't prove this. And also, if you think about it, subtraction also doesn't have a proper neutral element. It has a neutral element for the second input because anything minus 0 is itself, but that doesn't work for the first input. 0 minus anything is not itself. Okay, so this has been a bit of a strange video where I'm basically explaining some maths. So in the next video, I'm going to justify this by coming back to programming, and I'm going to tell you about the reduce function and why it's important.